This is problem 7-36. It's on page 400. An insulated piston cylinder device contains 5 liters of saturated liquid water at a constant pressure of 150 kilopascals. An electric resistance heater inside the cylinder is now turned on and 2200 kilojoules of energy is transferred to the steam. Determine the entropy change of the water during this process. Okay, so it's an insulated piston cylinder device. Let's draw it in both states. Here's state 1. Probably need a little more space than that, so let's move it up a bit. There's saturated liquid water. So if this is state 1, that means that the quality in state 1 is 0.0 because it's saturated liquid. The volume is initially 5 liters, which is 0.005 cubic meters. I ran out of space, I have to put it on the outside, but anyway, it's 1,000th or 5,000ths of a cubic meter, and the pressure is 150 kilopascals. Make sure that's correct. Yeah, 150 kilopascals. Now there's an electric resistance heater where electrical work is put in the amount of 2200 kilojoules. Now this work, when it goes through the coil, is going to be transformed into thermal energy or heat. And that's an irreversible change. So we expect for there to be some increase in the irreversibility here. Anyway, so there's no heat transfer, and of course boundary work is going to come out of this system because as the liquid boils off, then the system is going to expand. It's going to do boundary work against the atmosphere. Now in state 2, we're not sure if all the liquid boils off or not. We don't know yet. But for now, let's just assume that it doesn't. And of course, the pressure in state 2 is the same as the pressure in state 1, which is 150 kilopascals, because this is a piston cylinder device. We're just supposed to find the change in entropy of the system. Well, at state 1, it's pretty easy to find the specific entropy because we know in state 1, we know the pressure, and we also know the quality. So if we want to find something like the entropy in state 1, it will just be the entropy of saturated liquid. So all you have to do is go look it up. So go to the back of your book to the saturated tables for water and look up the entropy of saturated water at a pressure of 150 kilopascals. When you do that, you'll find it's 1.4336 kilojoules per kilogram per Kelvin. And while we're there, we'll look up the enthalpy and the specific volume because we're going to need those later. The enthalpy is 467.11 kilojoules per kilogram. Of course, this is just HF. VF is just 0.001053 cubic meters per kilogram. Still roughly 1,000 kilograms per cubic meter of density. All right, now, we need to find the entropy in state 2, or the specific entropy in state 2. How on earth will we do that? Well, to find the entropy in state 2, we need to know something else about state 2. We know the pressure in state 2, but we don't know anything else. In fact, we don't even know if all the liquid was boiled off. It could be that it was all boiled off. It could have gone well beyond the saturated state. It could be superheated. We don't know. How would we figure that out? Well, we know how much energy was put into the system. And we could ask the question, was this enough to boil off the water and to provide all the boundary work that would have had to take place? In other words, we need an energy balance here. So let's take care of that next. Now, the energy balance would say that the work that goes in, which is all of this 2200 kilojoules, changes the account balance. Let's see, let's write it. Let's see, how do I want to, let's start from the regular energy balance. Heat transfer in minus work out, and these would be net amounts, equals the change in internal energy of the system. This is just our closed system energy balance. Okay. Now, obviously, there's no heat transferred in, and this work out, well, there is boundary work out, but there's also a negative work in that we can consider work out. In other words, there's work that flows in and work that flows out. This work is just the net term. It's the total of the two. Okay, I'm not particularly fond of this energy balance. A better way to write it, in my opinion, is like this. Q in minus Q out plus W in minus W out. And that makes it really easy to see. These are just deposits and withdrawals. We don't have to worry about a signing convention anymore. And so then you see, since we have no heat transfer, then the work transfer in, well, then we don't have to mess with this minus minus stuff. We can just say the work that's transferred in is just this electrical work. Let me put an E here so we can evaluate it as electrical work. See, that's this term. That's the work that comes in. The work that goes out is just boundary work. And to me, conceptually, that's a little easier to think about and understand. Now let's expand the right-hand side too, because that's just the account balance change, right? You deposit energy, some of it stays in, some of it leaves, right? That's what this says. There's a deposit and there's a withdrawal. But what happens is the amount of energy in the system changes. So we can write that as the mass times the internal energy in state 2, less the internal energy in state 1. This is just evaluating how much energy there is, but writing it down on a specific mass basis. All right, so what are we really interested in though? Well, we're interested in state 2. Now, we could go this way, right? We could evaluate the boundary work because the boundary work would just be PdV, P delta V. But remember, when the boundary work is boundary work at constant pressure, we can combine it with the account balance change. And when we do that, what we'll end up with, just moving this to the other side, what we'd end up with, well here, let's do it one step at a time. The electrical work equals M U2 minus U1 plus boundary work. And remember, this comes out as mass times enthalpy change between states 2 and 1. I'll let you prove this. We've gone through this several times. Substitute in P delta V and see what happens. You can get to this point, okay? Now, the system does not hold enthalpy. This is just a trick. This is just a way of combining the account balance change with the boundary work withdrawal. That's all it is. It makes our lives a little easier because now all we have to do is find the enthalpy in state 2 from the energy balance. And to do that, it's simply the electrical work per unit mass, okay, plus the enthalpy in state 1. So we need to find out how much mass is in the system. So let's go off and do that. The mass in the system. How would we do it? Well, we know the total volume and we know the specific volume. So we could take the total volume divided by the specific volume. That would give us the mass in the system. So that's 0.005 cubic meters of volume divided by 0.001053 cubic meters per kilogram. This is going to be what? About 5 or so, a little less. In fact, it comes out to 4. You know what, let me write it over here. The mass in the system we've just computed, I'll just write it up here because it's the same in both. From here, it's 4.7483 kilograms. And we just got that from taking the total volume in state 1 and dividing it by the specific volume in state 1. So you see the units, the cubic meters cancel when you get kilograms of mass. So there's the mass. That was pretty easy. The electrical work then is 2,200 kilojoules, and that 2,200 kilojoules goes into the almost 5 kilograms of mass, the 4.7483 kilograms. And we have to add to that the enthalpy in state 1, which we found as 467.11 kilojoules per kilogram. When you plug that in your calculator, you'll find that the enthalpy in state 2 is 930.43 kilojoules per kilogram. Now, we have two properties, right? We've got the pressure in state 2, and now we have the enthalpy in state 2. So if we take the pressure in state 2, still 150 kilopascals, together, then we can go to the back of your book, and what you'll notice is that the enthalpy in state 2 is less than the enthalpy of saturated vapor, and it's more than the enthalpy of saturated liquid at 150 kilopascals. You should go there and look it up. You should be working this homework on your own, or by the time you get to this point, you should have already had an idea of what was going on here, and you're just checking to see if you're right. But here's where you end up. The enthalpy in state 2 is less than the saturated vapor enthalpy at 150 kilopascals, and it's more than the saturated liquid enthalpy at 150 kilopascals. What that means is we've got a saturated mixture, so we need to calculate the quality. I'm going to change colors. This one seems to be running out of ink. So we can calculate the quality in state 2. We know it must be saturated because of this. So this would be the enthalpy in state 2 less SF over HFG, the enthalpy between the two, saturated vapor and liquid state. So this is 930.43 kilojoules per kilogram. We already know that. Less HF, we already know that's 467.11 kilojoules per kilogram. That was just the enthalpy in state 1, which is just HF. It's not because it's state 1 that I'm putting it in here. It's because it's HF at 150 kilopascals. And you have to look up HFG, just the difference between the enthalpy of saturated vapor and liquid. For whatever reason, I didn't do that. I plugged in HG and HF. So here's HG, 2693.6 less 467.11. I could have just looked up HFG in the table because it's there. Anyway, all these are kilojoule per kilogram units. So we'll get out the quality as a fraction. Of course, it has to be less than 1. If you get a number more than 1, you've done something wrong. Or if you get a negative number, you've done something wrong. Anyway, this comes out to about 0.208094. So what does that mean? Well, that means about 21% of the mass is in the vapor phase. And I've drawn this wrong, right? Because the vapor phase is going to take up a whole lot more volume than the liquid, even though most of the mass is still in the liquid. But as mass percentage is not so bad, I guess. Okay, as volume percentage is terrible. So now what? Well, now we should be able to find the entropy in state 2. Okay? So let me erase this. We don't need it anymore, really. All we really needed to do was find the quality in state 2. And now we can calculate the specific entropy in state 2. It would just be SF plus X2 SFG. Okay, so that is 1.4336 kilojoules per kilogram per Kelvin. Remember, we looked that up before. Okay, that was the entropy in state 1, and the reason it was the entropy in state 1 is because it was the entropy of saturated liquid at 150 kilopascals. So I'm plugging it in here, not because it was the entropy in state 1, but because it's the entropy of saturated liquid at 150 kilopascals. So now add to that the quality, 0.20809.4 multiplied by SFG, which they do have conveniently for you in the table. It's 5.7897 kilojoules per kilogram per Kelvin. Okay, multiply all that out, and you'll find that the entropy in state 2 is about 2.6384. You have to round it off somewhere. So kilojoules per kilogram per Kelvin. There's the specific entropy in state 2. Now, why would we care about that? Well, we were asked to find the change in entropy. Now, this would be the change in total entropy. So this is a delta capital S. This would be the mass multiplied by the entropy in state 2 less the entropy in state 1, where these are the specific entropies, the entropies per unit mass. Okay. So, 4.7483 kilograms changes entropy, ends up at 2.6384, began at 1.4336. And I'm sorry if I'm off the camera, this is just kilojoules per kilogram per Kelvin, and so the kilograms go away. We'll get kilojoules per Kelvin. When you plug it into your calculator, this comes out to about 5.72 kilojoules per kilogram. Okay? Now, you may look at this and say, you know, I didn't understand all this. I did it a different way, and I got exactly the answer at the bottom of the page. So let me show you how you can do that. There's actually a really short way to get the entropy change. You'll notice that if you take the work in and divide it by the absolute temperature of the system. That would be 2,200 kilojoules. And look up the saturation temperature. So look up the saturation temperature. Turns out that the saturation temperature is 384.35 Kelvin. Of course, you'll have it in degrees Celsius by looking it up. But convert it to Kelvin. So divide this by 384.35 Kelvin. You'll find that you get exactly 5.72 kilojoules per Kelvin. Now, why on earth does this happen? How does this happen? Well, notice that the temperature of the system is constant because the pressure is constant. So since we're at saturation, the temperature has to stay constant. Essentially what we're doing is transferring heat isothermally, right? We're boiling off some water. This is not a totally reversible thing, but it's an internally reversible thing. Okay? So if we simply divide the heat transfer, if you will, by the temperature at which that heat transfer takes place, we get the amount of entropy carried into the system. This is really not such a big surprise because the boundary work that comes out does not carry entropy with it. Remember, work doesn't carry entropy with it. So you can look at this and say, well, okay, so this work didn't carry any entropy out of the system, but didn't this work not carry any entropy in? Be careful there. It didn't, but the current went through a resistor, which was irreversible. So it was as if we transferred heat into the system, and heat does carry entropy with it. So that's why this works out. Really what this is Qn over T, where the temperature is constant. You can look at this and say, well, why didn't you just show us this in the first place? Well, the solution I showed you was more general. It's also interesting to note that the results are consistent and therefore more likely to be true. Okay, but you need to understand both paths. You need to understand both methods of solving this problem.